Hello, everyone. I am George Tzanetakis, and I'm a professor in computer science at the University of Victoria in Canada. This is the third part of a series of videos for the statistical and relational artificial intelligence for music tutorial of the European Signal Processing Conference. So in the previous two videos, we looked at the importance of learning and the importance of rules in the analysis and creation of music. And more specifically, we looked at some specific examples, the scattering transform, the sound types, both examples of different type of representations, as well as computer-assisted or computer-aided orchestration, which is a problem that shows how rules and learning can be integrated into a system. In this part of the talk, we will move further in that direction and discuss approaches to music modeling that try to combine these two aspects in a more natural and homogeneous way under one formalism. So I will now share my screen and start going over the slides. Okay, so, I will be talking about basically how we can combine learning, logic, and probability to give us a unified view for musical signal processing. So we have an explosive growth in the amount of data collected in the business and scientific world. And the topic that we're really interested in this tutorial is music. So when you look at data about music, as well as many other domains, it exhibits two characteristics. One is uncertainty, and the other is complex structure. And uncertainty comes from many sources. So there can be noise in the data, for example, bad recording conditions in music. There can be misspellings. And there can also be incomplete information. We might not know part of the information that we need. And there is also relational complexity. So we have situations that involve multiple objects, classes of objects, and relationships between them. So for example, when analyzing text, we want to know what type of word is a particular word. Is it a verb? Is it a noun? We want to know relationships. For example, that a particular word is an author of a publication. There's similar relationships in music. There's as we have seen in the previous two talks, there's a lot of different relationships in time, relationships in structure, hierarchical relationships, and this introduces complexity. So in the previous two talks, we talked about acoustic complexity and relational complexity in the context of music. So, the real challenge is how can we make artificial intelligence systems that are capable of dealing with both aspects? And can we, in doing that, can we move towards approaching human intelligence for making sense of this data? And most likely you are familiar with dealing with one or the other aspect, because in the majority of existing work, we focus either on dealing with uncertainty and large amounts of data, for example, in areas like deep learning and machine learning. And in other fields, we focus on relational complexity, something like databases or the semantic web or logic and first order logic. So in this third part of the tutorial, we will see how we can address both of these two aspects. So let's look a little bit more into this sort of dimensions of logic and probability. So here we have this diagram where for logic deals with atomic things, with explicit enumeration. And if we extend propositional logic to first order logic, it deals with relationships between these objects. So we can say things like every human is a mammal, and then George is a human, therefore George is a mammal, that type of reasoning. And then probability is the best mathematical abstraction we have to deal with uncertainty. So whether that's sensor noise, human error, inconsistencies, unpredictabilities in the system, the way we can get a handle on them is through probability. So in most cases, these two aspects are treated separately. So probability is the standard way to represent uncertainty in knowledge, and logical representations are the standard way to represent knowledge and complex relational information. So, so there's not a lot of work in combining the two. And if they are combined in a kind of ad hoc way, dependent on the particular problem, and potentially using very different tools and software environments. So this is kind of the challenge that we will try to address in this tutorial. So the emerging field of statistical relational learning combines ideas from probability, logic, and learning. So there's a couple of different models within that space. So there's probabilistic logic, probabilistic relational models, probabilistic inductive logic programming, and the one that we will talk a little bit more in this tutorial are Markov logic networks, which were introduced about 15 to 20 years ago. So what these techniques do is they combine ideas from probability and statistics to address uncertainty, as well as tools from logic, databases, and programming languages to represent structure. So you can view them as a hybrid between these two usually different domains that are treated separately. Okay, so, oops, wrong direction. So why use a relational model? Well, because with a relational model, what we can do is use information about one object to help us reach conclusions about another object. So for example, if we analyze information in a database about papers and authors, we are able to associate perhaps a particular word with being an author, and then being able to tell that two different spellings of the same underlying author refer to the same object. And that type of reasoning is quite hard to do when you use a black box machine learning system. So what we want to be able to do is propagate information about the topic of a document to documents that are linked to it, and documents that it links to. And that information should sort of spread and propagate in a way that's structured and also is able to include uncertainty. So why are we interested in using a relational model in music analysis? So in most music information retrieval applications, the data of interest is structured, and it contains complex relational dependencies, and we have already covered some of these dependencies in the previous two videos. So for example, a common task in music information retrieval is chord progression estimation. So we're given a set of notes, or sometimes even just the audio signal, and what we want is a sequence of symbols which denote different chords. So here you can see we have an F minor and different symbols for the chords. And also these symbols underneath are what are called functional analysis. So it's a more detailed analysis of not just what the chords are, but what their function is in harmony. So for those of you who have some background in music, that will be known stuff. For those of you who don't, I don't have time to go into detail, but suffice to say that there is a very rich structure in this type of annotation. And this type of annotation is not trivial. Even for somebody trained in music, sometimes there can be the same set of notes might be labeled with two different chord symbols depending on how it functions in the surrounding context. The traditional approach to solving the chord estimation problem is we compute some low-level features from the audio, for example, the chromogram, and then we use a hidden Markov model. And the states in the hidden Markov model are the chords, the observations are the low-level features, and the hidden Markov model kind of deals with two things. It deals with modeling the probabilistic nature of the relationship between the chord and the low-level features. So we have many possible low-level features that map to the same chord. And then the transition probabilities capture the time dependencies, so the fact that certain chords are more likely to follow other chords in time. So you can get some good results with this model, and it's kind of the most traditional way of solving this problem, but there's a lot of rich logical structure of the underlying data that is not taken into account. And when using an approach like hidden Markov models, it's much more difficult to handle a complex task such as functional analysis, because in functional analysis, frequently what you will do is you will label one chord, and then that will influence how you label another chord that's before it, and then that will influence another chord that's after. So there's all this jumping in time in a very complicated way that is very structured and has a lot of rules. So that's one of the challenges that we would like to address in this tutorial. There's other applications in music information retrieval where the data is structured to begin with and has complex relational dependencies. So here you see a network analysis, a graph analysis, where it shows influence graphs so we can understand how sampling works. So you can see that a lot of hip hop samples from soul, funk, and disco music, but it samples less from classical music, and kind of visualize these relationships. So there is all this structure. How can this structure be modeled? And that's where statistical relational learning techniques can come handy. So another area where having a relational model can be useful is when we perform multimodal music processing. So that's when we have a lot of different complementary sources of music related information. So for example, we might have the audio signal, we might have structure annotations, and we might have lyrics. And the idea is, how can these type informations connect to each other, align with each other, and then how can we use them to interact with the system? So how can we build systems that address what the user needs and how it behaves? So lyrics to audio alignment, we want to estimate the relationship between the lyrics and an audio recording, which is an acoustic representation. So we are able to sort of see when the lyrics happen in the audio recording. That's an example of multimodal music processing. So the goal of statistical relational learning is to represent, reason, and learn in domains with complex relational and rich probabilistic structure. There's many different approaches and they have different characteristics. So here you see a whole bunch of variants of these techniques, from relational Gaussian processes, infinite hidden relational models, to Markov logic, to probabilistic entity relationship models, and so forth. So a good book to get a review and survey of this field is listed down here, Introduction to Statistical Relational Learning, and you can go there for details. But in this tutorial, we will focus on only a few of these approaches and try to just give you a flavor of the ideas and how they work, and connect them with the topics that we have been discussing about how rules and learning are important in understanding music and how we can combine rules and learning. So Markov logic networks are one of those formalisms. And the nice thing about them is that they're kind of an umbrella formalism. So they combine first order logic and probabilistic graphical models, which makes them quite flexible. So the basic idea is that we use first order logic to specify in a compact way models of complex network dependencies between variables, which are probabilistic graphical models. And many of the specific statistical relational formalisms can be seen as particular cases of MLNs. Now that doesn't mean that MLNs can replace everything, and there are cases where you might prefer using one. So for example, just to give you a specific example that we will go over later, a hidden Markov model is a special case of an MLN. If all you need is a hidden Markov model, there are more efficient, clean ways of implementing it, but then you're limited by what it can model. Whereas if you use it in an MLN context, you can start with a hidden Markov model and then kind of make it more complex and add more things to it. So some of the appealing features is there's rapid progress in developing scalable and robust learning and inference algorithms. So you can learn very large networks and carry inference in very large networks. And they provide a way to incorporate a wide range of domain knowledge. So that's one of the challenges with black box systems, like a deep learning system, is that the only way we interface with the system is by providing labeled data. And if you want to include some domain knowledge, it's very hard to add that knowledge to the system in a way that is easy and clean. And there's also the idea of transfer learning, where we want to have domains that maybe not have variables in common, but share structure, and we will get back to that. So, so just to look a little bit at what is the state of the art in music information retrieval, for handling uncertainty of audio, probabilistic graphical models have been used in many different ways. So there is hidden Markov models, which have been used for chord estimation and beat tracking, but they can only express limited time dependencies. And that has led to other formalisms like conditional random fields or tree structures or n-grams that capture a little bit more complex dependencies. But they kind of work at a simple level, and it's hard to combine knowledge at different levels of musical structure. So we know that a lot of the music attributes interact with each other. The location of beats influences where chords are detected, the structure of a song, knowing that two sections of a song are verse, also imposes constraints on the chords used. And there are all these different time scales. There is the level of the note, of the beat, of the phrase. And again, there's multi-modal information, so lyrics and melody and accompaniment. And there's also changes in music expression. For example, beat tracking might not provide a regularly spaced sequence of beats, but might change over time. So probabilistic graphical models can only get us part of the way to where we want to be. And on the other side of the fence, we have logic frameworks. And logic frameworks allow us to model musical rules in a compact and human readable way. So they're closer to what, if you learn music theory and you're taught harmony, you're taught certain rules about how certain chords function or how certain intervals work in a particular context. And these rules can be much more easily expressed in the context of logic. So for example, if we can have a rule that if I have a C major chord and it's the first degree, that implies that we are in a key of C major. Inductive logic programming combines logic programming with machine learning and has been used to model music rules. So there's some work on harmony characterization, expressive music performance, but most of these logic approaches rely on symbolic representations where you know what notes are playing and you don't have, they're kind of already highly structured representations. So in the previous talks, we looked at the fact that for analyzing audio, we need to use projective transformations. And these sort of representations, you can think of them as a type of transcription. So you have an extra step, and that extra step makes them not applicable immediately if you just have an audio recording. So there is some people believe that a lot of MIR tasks are converging to a performance plateau. It's definitely the case that for many tasks, the gains in performance have over the years become smaller as people get better and better at developing algorithms for the particular problem. And a lot of the more recent approaches use deep learning techniques because they can use learned features. They can encode sometimes longer musical structure. But in many cases, the output of a neural network has to be post-processed. So for example, in these two papers on beat tracking, there's a dynamic Bayesian network that is used at the end step to do some post-processing related with getting more musically meaningful results. So I hope that, essentially we spent the last two videos arguing for this, but to deal with music-related material requires the ability to handle both rich probabilistic information, so noise, uncertainty, and incomplete information, as well as complex relational structure. So this is what will motivate our development of the techniques that we will discuss. So before doing that, I would like to give you a little bit of an overview of Markov logic networks. And I imagine that coming from a signal processing background, a lot of you perhaps are more familiar with probabilistic graphical models, specific things like Kalman filter or the hidden Markov models. So let's try to connect these concepts because that will set the foundation for learning about this topic. So the basic idea of a probabilistic graphical model is that many, and we will discuss it in the context of music, is that we have a set of input random variables and a set of output variables to be predicted. The input random variables are called observations, and the output random variables are what we are trying to predict and are called the hidden states. And the popular approach is to specify a probability distribution to select the most likely class Y given an observation X. So if I tell you certain things about the problem, so if I tell you the chroma vectors for an audio recording, that's the set of input variables, you will predict the most likely values for the variables that are the chords of the song. So the interesting thing is that in a probabilistic graphical model, the set of X and Y variables has a complex structure. And in a graphical model, you have edges that show which variables influence which variables. And that's kind of the idea. So there are some really nice books by Daphne Keller and I know his first name. I should know it. Anyway, Kevin Murphy. Kevin Murphy, for that you can look at to review this concept. So a common example of probabilistic graphical model is directed graphs or Bayesian networks, and the well-known hidden Markov model is an example of such a graph. So we have the states, y1, y2, y3. Each of those variables can be a chord, and then we have the observations, which are what we observe. And you can think of the hidden Markov model in a generative fashion. So if we know that we have, let's say, a C minor chord, that will produce a probability distribution. If we know, that will produce a certain randomly different types of observed chroma vectors. So it computes the joint probability between the sequence of hidden states and the sequence of observations. So this is here. And a hidden Markov model can be specified by using three probability distributions: a distribution over the initial states, the state transition distribution, and the observation distribution. But there are certain restrictions. So each observation variable, so what you observe at a particular time instance, only depends on the current state, and each state only depends on the previous one, and that's the Markov assumption. A more general probabilistic graphical model that has been used in music information retrieval is conditional random fields. And conditional random fields, you know which variables will be observed and which will need to be predicted. So you know which ones belong to X and which ones belong to Y. And it's kind of an undirected graph or a Markov network where there's not a direct influence, but there's sort of a more a relationship where you have rich overlapping features to calculate the conditional probability, the probability of the states given the observations. So in some ways they're similar to a hidden Markov model, but they're more suited to include rich overlapping features. So you could rely on both onsets and chroma features for downbeat tracking. That would be an example where you could use a conditional random field. So a Markov logic network is a set of weighted first-order logic formulas that can be seen as a template for the construction of a probabilistic graphical model. And if you're familiar with logic, typically you encode the things that you know in formulas, and that's called the knowledge base. So this can be seen as a set of hard constraints on the set of possible words. So in a first-order knowledge base, if a word violates even one formula, it has 0 probability. In real world, the logic formulas are generally true, but not always. So for example, if you said something like, all birds have feathers, and then said penguins don't have feathers, in a kind of traditional first order knowledge base, penguins could not be birds because that would be a 0 probability. But in Markov logic, these constraints are softened. So you could say that 90% of the time birds have, it's not of the time, but you could say that the weight of the rule, all birds have feathers, is 0.9. And that might be, and that weight reflects your confidence in that. So here's an example of a small toy knowledge base. You could say a major chord implies a happy mood. So this in first order logic, you would write for every x, is major x implies is happy mood x. And that rule has a weight of 0.5. And here, if two chords are neighbors, either the two are major chords or neither are. So this is just expressing this relationship. And notice that these relationships have variables. So x is a variable. When we apply the formulas to specific constants, like the C major and G major chord, then we get a network. So this network is constructed, is kind of created by applying these rules to these constants, and it shows these relationships. So we know that C major is a major chord, and because it's a major chord, we also know that it has a happy mood. And we know that G major is a major chord. So we know that they are neighbors. And notice that there's two instances of they are neighbors because it's a symmetric relationship. So when X is GM and Y is CM, and when X is CM and Y is GM, and so forth. So so once we have that, now we actually have a probabilistic graphical network, and we can use techniques from probabilistic graphical network inference to do reasoning with this type of network. So MLNs are meant to be intuitive representations of real-world scenarios. And typically what you do is you express what you know about the problem using first-order logic formulas. Then a Markov network is constructed by instantiating these formulas. And then the knowledge base is transformed into a probabilistic model by assigning weights to the formulas. And these weights can either be assigned manually based on what you think, or they can be learned from data. And finally, inference is performed on the resulting Markov network. And the inference is finding query-given evidence. So you can answer questions about your problem using inference. So a Markov network is a model for the joint distribution of a set of variables. And a potential function here, we would, you could write it this way. This is the probability that a particular variable v has a value lowercase v. And in MLNs, we use a log linear form where all these are expressed with exponentials. So you can, so just understand this, let's look at an example of construction. Let's say we want to construct an MLN about chords with two formulas. One formula is that a major chord implies a happy mood, and the other formula is that if two chords are neighbors, either both are major chords or neither are. So this is how these can be expressed. We have three predicates. So is major, is happy mood are neighbors. These are our predicates. And two constants. The constants, in this case, we just have two constants, C major chord and G major chord. So because there are 8 nodes in the resulting network, so if you go back here, we have 1, 2, 3, 4, 1, 2, 3, 4, there's 8 nodes. Then we know that these are, each random variable is a binary random variable. So there's 2 to the 8 possible worlds. So a world in the context of logic is an assignment of values to these variables. So that's the process. And the grounding process is replacing the variables with constants. So this is the ground Markov network obtained by applying the first formula to the constant C major chord and G major chord. So we first replace it in the first part of the rule, and then we add these edges, because the edge and the new node, because that's the rule. So we result into two cliques with these two things, and they will have weight W1. So again, this is an example of the full construction. So this is important, that the Markov logic network is a template. It's kind of a sketch for how to construct a Markov network. If you give it a different set of constants, it will produce a different network. And the network grows as the number of constants increases, but the number of the formulas or the templates remains the same. And what it does is it specifies a joint probability distribution over a set of possible worlds V. So like I said, a world is an assignment of values to each possible ground atom, and the probability of a possible world given by this is given by this equation. So, and Ni counts the assignments which make Fi true. So here, for example, we have the value of V is all these different, so let's say, you know, we have most of them are true except this one. So this is, all these are true except this one. Then we can compute what is the probability of this example given this network. So it's a way of computing a joint probability distribution. Now notice that because of the network structure, we can compute this efficiently, and we don't need to calculate every possible combination. So if you want to use an MLN for inference, for a labeling task, you know which predicates are evidence and which will be queries. So what you do is you kind of separate them, partition them into evidence, observations, and query atoms Y, and then you can write the conditional probability of Y given X using the same set of, the same kind of formula. So this is the formulas that contain a query atom, this Fy, and the Ny here is the number of true groundings of the ith clause involving the query atoms. So that's how you can compute that quantity. So the main thing, if this is becoming a bit confusing, the key thing to remember is that using this formulation, it's a pretty general formulation. So we can translate any hidden Markov model or any conditional random field into an MLN formulation. So for example, if we're given an HMM, then we just have to model the system with three generic formulas: a state formula, a transition, and an observation formula, which says that if you are in state S at time t, the observation of time t will be O, and then this is the state transition. So for each one of those quantities, you will introduce a clause, and then the weight will be based on the probability of the HMM. So here you notice that the weight is the log of, this is the transition probability of the HMM, and this is the observation probability of the HMM. So it's a complete mechanical almost mapping where we can take the probabilities that specify an HMM and put them in this logic formulation, and then they will be equivalent. So most probabilistic graphical models can be viewed as a particular case of MLN. So that includes Markov networks, log linear models, conditional random fields, hidden Markov models. And the nice thing is that this allows a unified representation that's complex and very clean. So, you know, you can imagine that if you had, let's say, a system where it was doing beat tracking using HMMs and chord detection using conditional random fields, you might have some software in MATLAB for doing the HMM and some software in another language like Python for doing the CRF, and then some other software that combines the results. And each one will be specified in a different way, whereas with MLNs, everything is using a unified language. Another thing that's really important is that it facilitates the incorporation of rich domain knowledge that can be combined with purely empirical learning. And that is a very key advantage of techniques like that. So for example, if I have a song and I know some of the chords, let's say I have an application where I'm trying to figure out the chords to a song, and for some I'm pretty confident I got them, but some I don't know. In existing chord detection systems, there's no way for me to give that partial knowledge into the system. Whereas with a Markov logic network knowledge base, I could just add a clause, a formula to that effect, and then everything would kind of work. So you can reason with incomplete data. You don't need everything. And if you want to have first order logic, you can take any first order logic problem and convert it to an MLN by making all the weights equal. So then that way you can easily model logic. So there are cases where you can merge different knowledge bases, even if they're not completely compatible, because they speak that same language of logic. And also it allows contradiction. So that's something really important in music, is that a lot of the rules about harmony are not always obeyed. There are pieces where some of the rules are violated. And so having the ability to kind of have that ambiguity can be really important, but still retaining it's sort of a probabilistic soft view of these rules. So this kind of gave you a quick crash course in Markov logic network. So now let's move into a specific music example and see how they can be used. And this is the multi-scale tonal harmonic analysis of music. So this is work that looks at the mostly at the estimation of chords, but also the estimation of key, as well as the idea of a structurally consistent chord estimation. And we will explain what that is. But the main takeaways is that we can get exactly the same results as we would get with hidden Markov models or conditional random fields when we use MLNs. But once we include dependencies, relational dependencies, we can outperform these traditional models. So, so it's basically, now you might say, well, this sounds too good to be true. And that's to some extent a correct statement, because there are some disadvantages, and I'll talk about that. But probably the one that I should mention right off the bat is that they are much more heavy computationally. So if you use an MLN to solve chord detection in a way that's equivalent to a hidden Markov model, it will be slower because it's a more general formalism, whereas the hidden Markov model takes specific advantage of the structure to come up with a very efficient algorithm. So as computers are getting more and more powerful, this is not a stopper, and especially, you know, these days people are running really heavy learning tasks with deep learning. So the time that these models take to do inference is quite reasonable in the modern computing context. So let's look at an example. So this is an example where we have this hierarchical kind of temporal analysis. So we have verses, so these are denoted at the bottom, and every verse contains a number of measures. Every measure contains a number of beats, and for every beat we have observations of chroma values. So these are features that are extracted from the audio signal and show the energy of different chroma or pitch classes over time. And then we have chords, which are for each beat we have a chord, and then we have a local key that is actually every 4 chords that influences the chords. And here you see some of the arrows denote kind of influence. So this sort of shows you all these layers of information. So let's look at how these layers of information can be kind of encoded using logic. So the first formula is that each chroma feature is generated by a chord. So this shows that for a chord at time t, it generates a chroma value at time t. So this is, each chroma feature is generated by a single chord. Now, this one, so this is the observation probabilities that, let's say, a hidden Markov model will have. This one is the transition probability. So this logic rule says that some chord traditions are more likely than others. So, and it's encoded in the weights. So notice that this one is for a successor of the beat at time t1 and t2, a certain chord at time t1 implies a certain chord at time t2. So here we have, this will result into a lot of different pairs of chords, including self-transitions, like going from one chord to its own self. And those are equivalent to the transition probabilities. Now, there's also expressing that chords and keys are interrelated. So the local key, the key in the 4 beats, influences what the chord in each bar will be. This one shows that key changes outside downbeats are unlikely. So the key will most of the time change at downbeats. But notice that because it's a weight, it's not an absolute statement. It allows for exceptions. And it's this allowing for exceptions that's really important in the expressivity of this formalism. And then finally, we have the fact that same segment types are likely to have similar chord progressions. So if you have a verse and a verse, then most likely the chords in the verse will be the same. So all this complex structure, all these kind of arrows are encoded into these logic statements. And I don't have to explicitly enumerate every possible combination. These are just used to generate every possible combination. So it's quite elegant and expressive. So this is the input file that kind of shows how you encode that. So here you see that the prior probability for 3 chords, they are all equal. In this case, we just deal with 3 chords. And here we have observations, transition probabilities. So it's quite, basically that is your knowledge base. You give that file and that is what you know about the problem. And then you have an evidence database. So the evidence database would say that for a particular song that you're trying to predict the chords, here are the chroma observations. So chroma 0 is observed at the first 2 frames. This is the order of the frames belonging to the same measure, and frames belonging to the same structure type. So one is kind of the rules, the other is the evidence that you have. And to perform inference, you can basically specify the input MLN file, the input database, what are the query variables, so state and key, and what are the evidence, and you get the results. So you have the evidence DB, the output file, the query predicates, and the output will look something like this. So the key for the stuff, the state, and so forth. So this is how we can predict key and chords using a Markov logic network. So another example would be partial evidence. So let's say that we know some of the chords, but many of them we don't. So we can just add the chords that we know. And if you do an HMM-like MLN, you can increase the results. Like originally when no chords were known, were 60.5. But if we add 10%, it doesn't go to 70%, but it goes to 76. So the addition of the chords increases, helps improve other chords that were unknown. And that's exactly the type of partial knowledge that systems like a black box deep learning framework are not able to handle. So we'll talk a little bit more about the MLN. So when you have a problem, you first design an MLN, then you learn the parameters and the weights or the graph structure. So this is the part where here, notice that we have these values. So how do we learn these values? That's a key question. So if, for example, we knew, for the chord transition probabilities, we could analyze the data that we have and compute these chord transition probabilities. So we could find out, look at our data and find all the cases where a C major chord follows a C major chord, add them up, divide them by the total number, and give a weight. So these weights can either be manually specified or learned. And finally, there's two types of inference. There is the most likely state of the world consistent with some evidence, or there's arbitrary conditional probability. So what is the probability that formula F1 holds given that formula F2 does? That's another type of inference. So translating a hidden Markov model or a CRF to an MLN, it's one-to-one correspondence. You can basically take the probabilities and convert them to weights in the MLN in a kind of straightforward fashion. However, in the more general case, the weights don't have a necessarily probabilistic interpretation, but the weights can be learned from data. And one possible way to set the weights is you write down the probability with which each formula should hold, treat these as empirical frequencies, and then learn the weights from them. So that's one way to go about it. In many tasks, for example, labeling, the goal is to compute the answer to a query. And there's a lot of different ways to do inference, and there's exact and approximate solvers. So when you have a large size network, doing exact inference sometimes is infeasible. But there are methods that combine probabilistic methods with ideas for logic inference that work quite well in practice. So there's a bunch of different algorithms. So for example, MCSAT and other, I'm not going to go into the detail, but basically these algorithms can be used to perform the inference that is needed. There's many ways that learning can be used in MLN. So the most kind of straightforward and common is weight learning. So this is kind of similar to learning the parameters of the classifier. We're given the formulas and we find the weights that maximize the likelihood or conditional likelihood of a relational database. So we analyze our data and count how many times the rule is true, basically. Like imagine that you have the labels of the chords and you're trying to find the transition probability of a chord. Like we said, you would just count how many times that rule is true in the knowledge base. What is a little bit more difficult and harder is structure learning. So it would be to learn the formulas themselves. And that's where typically still it's better to kind of do it by human input. So we understand the structure of the problem and we use it. And that relates to predicate invention, which is how new concepts can be discovered, and also transfer learning, how experience in one domain can help us learn faster in another through transfer learning. So I think like for most applications, we stick to weight learning, but it's good to be aware of these other types of learning. So in structured learning, both the formulas and the weights are learned, and there's techniques from inductive logic programming. So there's various ideas about how one can go about this. And one of the things that's nice about music is that we have a lot of knowledge from music theory. It's of rules and that have been developed. And these rules are rules that are expressed in language or certain kind of notation specific to music theory. But with a little bit of work, we can apply them. And because it's not a strict true or false situation, even if they are not exactly correct or we don't have all the details right, it still allows us to do some interesting systems. So I'm not going to talk about this. This is just how we can discover new predicates or new variables in relational databases. These are very important problems, but are also things that still there's not a lot of easy algorithms to use to do. And transfer learning is an important idea. The idea is to incorporate knowledge learned in one domain to improve learning speed or accuracy in a new domain of interest. Typically, this will be in domains with similar characteristics. So for an example from music, if we're doing chord detection for popular songs, we might just use the 24 major and minor chords. But if we want to extend that to jazz, jazz has a much larger vocabulary of chords. In a kind of standard approach, you would just train a completely new system for jazz. But is there a way we can take a system trained on pop music and adapt it to the jazz scenario? That would be transfer learning. Deep transfer is even more extreme, but it's the idea of kind of transferring in domains where the types of objects and variables are different. So I'm not gonna also cover that. I just wanted to give you some pointers to the literature. So in terms of software, there is the most widely packaged is probably Alchemy. It has different types of MLNs, and it has been used for a wide range of AI applications. Link prediction, entity resolution. There's documentation and examples. There's also TAFI, which is part of a relational optimizer for statistical inference. There's PI MLNs, which are part of the ProbCog toolbox, and it includes the toolbar 2 branch and bound exact inference algorithm and some other ones here. So I would say it's not as easy. These tools don't have the level of maturity that your traditional machine learning framework has, like scikit-learn, or deep learning framework like PyTorch or TensorFlow. But if you want to use them, they are usable, and you can try them out, and you can model your problem that way. So the problem of entity resolution is, given a database of records, for example, with video regions, determine which observations correspond to same real-world objects. So there is some work doing this resolution for Indian classical music, and there's a bit of work that's been done on Markov logic, where by taking advantage of the relationships, it exceeds the accuracy of supervised models. So some thoughts about Markov logic networks and deep learning. There is there's works that show a two-stage architecture where there's a deep learning network that performs a particular task, followed by a probabilistic graphical model that kind of introduces some more knowledge and domain knowledge and probabilities into the problem. And there's current work on using MLNs to define architecture of deep neural networks as a way to add knowledge to deep networks and learning with many levels of hidden variables. So there's some work on some product networks which allows fast probabilistic inference, and it's a deep architecture with full probabilistic semantics that's more kind of on the research stage. So I'm not sure if MLNs are the answer to everything. I think the field is still in flux, but I hope that we have convinced you that rules and learning are important aspects in music analysis, and we need some kind of formulation that is able to combine those two aspects in a clean and an elegant and expressive way. And Markov logic networks is one of the ways that that can be done. So to conclude, Markov logic networks are a powerful yet simple formalism for reasoning with uncertainty and complex relational structure. They encompass most currently used probabilistic and logic-based models, and they offer a more expressive and flexible but yet concise model for the processing of real-world data. There are many existing perspectives and directions of work, so I hope that this presentation will stimulate further research, development, and applications of MLNs to music, as well as other fields of signal processing. So this concludes the tutorial on statistical, relational, artificial intelligence in music. I'm honored to give this presentation on behalf of me, Carmine, and Helene, who prepared this tutorial. I would like to thank you. And I also would like to say that if any of you, we will be able to answer questions in the period that the tutorial is running in the virtual conference, but also don't hesitate to email us and contact us with any questions you have about the topics that we covered. So thank you very much and have a good time.